Okay, welcome back. This is AP Chapter 4, Lesson 2. And today we're going to talk about two things. We're going to talk about the difference between an electrolyte and a non-electrolyte. So what makes things electrolytes versus those that are not, and strong versus weak, and how we can actually calculate the concentration of our solution. That we'll be introducing a new term called molarity. So an electrolyte, you've heard of it before, you've seen Gatorade commercials. All that an electrolyte is a substance that when you put it in water will conduct electricity. So what substances are electrolytes? What substances will conduct electricity when you put them in water and what will not? We'll talk about that. So an electrolyte is a substance that conducts electricity when you put it in water. A non-electrolyte will not. Let's talk about who those are. So strong electrolytes are things that make the most ions, like salt. When you put it in water, it completely dissolves, it makes a lot of ions. So soluble ionic compounds are great electrolytes. Also great electrolytes are strong acids and strong bases. They're also really good conductors of electricity because they break down into a lot of ions. Weak electrolytes are weak acids and bases and things that weakly dissolve. Non-electrolytes are covalent things, okay? So, strong acids and bases are good electrolytes. Generally, the more ions you break apart into, the better the conductor you'll be. And strong acids dissolve completely. So, our strong acids, there's actually some missing. We have HCl, H2SO4, HNO3, so hydrochloric, sulfuric, nitric, perchloric. Those are all strong acids. Hydrobromic acid and hydroiodic acid are all strong electrolytes. If you could put hydrochloric acid in water and then look at it with your Miss Frizzle glasses, none of it would exist bonded together. None of it would be in the molecular form. It would completely exist broken down into the ions that compose it, which are H plus and Cl minus. Same thing with your strong bases. If you could put your strong bases in water and look at them with your Miss Frizzle glasses, they would not exist bonded together. Water would be able to pull them apart. And so this would exist as Rb plus and OH minus ions. We say that for every 100 of a strong acid or base molecule that you put in water, you have none existing in the molecular form. All exist in the ion form dissociated. More ions, better conductor. However, for a weak acid or a weak base, you actually have only about 1% dissociated. So 99 will exist as molecules and only 1 will be broken apart. Okay? Okay. So again, just to reiterate, the electrolytes that are strong exist mostly dissociated, not together. They don't exist as whole molecules. And those are your strong acids, which you have to memorize, your strong 6 acids. Your strong bases, you have to memorize your strong bases. I'll show you a quick way to do that tomorrow. And your soluble ionic compounds. And of course, there's a whole set of solubility rules so that we know if something's soluble or not. The weak electrolytes only exist about 1% dissociated. As ions, which is why they're weak. There's not a lot of ions there. And those are your weak acids and bases. So any acid or base that's not on our strong list. Things like acetic acid, vinegar, that's a weak acid. It stays mostly in its molecular form. Only about 1 in every 100 molecules actually exist as ions. Hydrofluoric acid, HF, is a weak acid. It exists mostly in its molecular form. Weak bases like baking soda or iron hydroxide, those exist mostly in their molecular form. And then we have non-electrolytes. And your non-electrolytes are your molecular substances, your covalent bonds. So mostly those things that are all nonmetals. Like sugar, right? That's C6H12O6, okay? Or any other type of covalent compound for that matter. Carbon dioxide, carbon tetrachloride, etc., etc. Those are all non-electrolytes. They don't conduct. Water, pure water is a non-electrolyte. It does not exist as ions. It exists as whole molecules stuck together. What you need to conduct electricity is moving charged particles, and these do not have them, these covalently bonded things. Therefore, they will not conduct electricity. Okay, so the final section I want to talk about today is section 3 in your notes, and it's about calculating concentration. What we use to express solution concentration is molarity. Its abbreviation is a capital M. And it really is an indication of how much stuff you have in a solution. Stuff in chemistry is measured in moles. So it's the number of moles of solute in a given liter of solution. And we have some practice problems here just to walk through together. So the first one says, calculate the molarity of a solution prepared by dissolving 11.5 grams of NaOH in enough water to make 1.5 liters of solution. They want molarity, okay? So what we're given here is 11.5 grams of NaOH, and we're given 1.50 liters of solution. We take a look at our numbers, and we always write down what we're given. After you've identified your numbers and what you've given, you write down what they are asking you. What the heck do they want? What's the question word? So they're asking you for molarity. And so now hopefully the next step is, what the heck is the equation for molarity? Molarity is equal to the moles of solute per liters of solution. So now I'll go back to what they gave me and see if I can plug anything in. They gave me grams of NaOH, which obviously is my solute because water is my solvent, right? Water is always the solvent. So NaOH is my solute. I cannot plug grams in there. That is moles. So I'm going to have to convert it to moles before I plug it in. But I can put the liters in the denominator of my solution. I have 1.5 liters. So before I can plug the moles in, I have to take the 11.5 grams that they gave me of the NaOH and convert it to moles by dividing by the formula mass. We know that 1 mole of NaOH always equals its formula mass in grams. And if you calculate the formula mass of NaOH, I think it turns out to be exactly 40 grams. 22.99 and 1.01 plus 16. So that turns out to 40 grams. So if we get our moles of NaOH here, I'll grab a calculator. We take 11.5 and divide it by 40. Whoops. Try again. 11.5 and divide it by 40. You should come up with 0.2875 moles. This is a classic example of you are not done with the problem, so this is not a step you should round at. You're going to use that answer up here. So I got exactly 0.2875, but if I did not, I would carry out that whole answer. Now I have the moles of solute that I've dissolved. I have the moles of NaOH. So in my molarity formula, I can just go ahead and plug this in, okay? So what your molarity formula should be then is 0.2875 moles, and we'll divide that by 1.5 liters. We did do this in Regents Chemistry. I know it's been a while, but the molarity turns out to be. Now here's where I'll pay attention to sig figs. Every number that was given to me was given in 3 sig figs, so I'm going to round this to 0.192. The units are moles per liter, or you can express that as a capital M, molar. Okay, that's how we would read it. Obviously, that's less concentrated than something that's 1 molar. The smaller the number, the less concentrated. And less ions. and less conducting electricity. Okay? Less concentrated. I think we have some other practice problems here. I don't see them there, so we'll do them together here. If we flip the page, I believe you have practice problem number 2 on the back. It says, give the concentration and type of each ion in the following solutions. And you have 0.50 molar CONO32. And for letter B, you have 1 molar FeCl04.3. Okay. So we have to think about, if they want the concentration and type of each ion, what this breaks down to when you put it in water. Okay? Remember, ionic compounds break down into the ions that compose them. This name is cobalt 2 nitrate. Therefore, this will break down into cobalt plus 2 ions and nitrate ions. Okay? This is completely soluble, as most ionic compounds are. And again, there will be a table of solubility rules. So if this started with 0.5 molar, and none of this, and none of this, this would go down by all 0.5. It completely breaks down into its ions. So if we could look at it in its molecular form, you would not see any molecules put together, only existing as ions. This will go up by 0.5 molar then, because there's 1 cobalt in every one of this molecule, and this would go up by 2 times 0.5 molar. So we would have 0.5 molar of cobalt ions and 1 molar of nitrate ions. And that's the answer to this question. Now, do you have to walk through all that? I say no. You don't really need to walk through all that. I just want to show you where we're getting those numbers from. So in this next example, if we have 1 molar iron perchlorate, since there's only 1 iron, we'll have 1 molar of iron ions. And since there's 3 perchlorates, we would multiply the molarity of the compound by 3. We would have 3 molar perchlorate ions. That is another way to look at it, okay? That is what you get for that example problem. And the next one, example number 3, I'm just going to write down what's given because you all have the paper in front of you. It says calculate the number of moles in 1.75 liters of 1 times 10 to the negative 3rd molar zinc chloride. Okay, so right off the bat, you should see they're asking you about chloride, but they're giving you information about the whole compound. So we're going to have to do a mole-mole to figure out chloride within the zinc chloride. We can get, since they gave us molarity and they gave us liters, we can get moles of the whole compound. Remember, molarity is equal to moles over liters. This time we have molarity, 1 times 10 to the negative 3rd. We do not have moles of the zinc chloride. We do not have moles of the whole compound, but we do have the liters of solution. So we can slap this over 1 and cross multiply. I'm just going to call that x. That would equal 1 times 10 to the negative 3 times 1.75. And if you multiply those, must be getting towards the end of the period. You should come up with 0.00175 moles. But that's of zinc chloride. So we need to relate that to chlorine. According to the formula, for every 1 mole of zinc chloride, there are 2 moles of Cl minus. So if you multiply that times 2, you should come up with 0.0035 moles of Cl minus. Okay? I think we'll call it a day there, and we'll do some practice and a demonstration in class tomorrow so that I'm sure y'all can understand this. Have a great night. Bye-bye, everybody.